Hi, let's start the analysis of the circuit W, right, using the VHDL electronic design automation tools, which is in our plan the method 4. So here you are the schema. This is the circuit to be analyzed. This is the equation that we will get, and from this equation we will translate the equation to VHDL, and then we will follow the synthesis process and the simulation process to get the final truth table. All right? Okay, so let's see if we can present the method 4, which is going to consist of using the electronic design automation EDA tools for developing circuits, So, and this is based on VHDL language. This is what we have in mind. We will use this example that we have now very well solved with 3 previous methods. Now we will try to solve it again, just for the sake of introducing the VHDL design flow tools, something that we will have here from P1 up to P8. So 2/3 of the course are going to be based on this utilization of VHDL tools. So yet again, another time, we have the entity and the internal architecture as usual now. So the point is that this circuit is going to be, transferred to the equation W that you know now by heart. This is the idea of the equation, but now instead of using, Wolfram Alpha syntax, we will use something which is quite similar, VHDL syntax, So we will start this kind of process down to the truth table, It is going to consist of several phases that I will go presenting my screen recording just now. But let me tell you the basics, The basics is that now, the equation is going to be transferred to a VHDL architecture. All right? So, this architecture is going to consist of basically a source file written in VHDL syntax. So the source file will have a name, for example, circuit W, but now VHD. This is going to be the source file. And using this source file, you see a single source file, that is okay for a circuit that simple. We will develop a project, all right? A VHDL project. And we will do that with free tools, and this means that we will have to go attaching the project to a given target chip, something that is real. And what is real here? For example, this kind of board, which is based on a complex programmable logic device type Max2 from Intel. This is a typical programmable complex logic device that you can see here in this room. This is the chip that you see, the big one, the squared one, is what is called a complex programmable logic device. And we have another one, right? This is not the only one that we've got. We've got, for example, another board for prototyping, and this is the DE10 from Terasics, and here you are the board the same, okay? And what you see here is basically another similar chip, a square chip which has hundreds of pins, but here you see some push buttons and some LEDs. You have a line of LEDs and some 7-segment displays, and a connection. Both boards has a connection to the USB, so they are going to be programmable using the right tool. So this is what we have in mind, developing a VHDL project for one of these chips, whatever it is, a Max2, a Max10, or a Cyclone 4, because there are many chips now in our labs available for downloading the project once it is finished. So once the project is organized around the project navigator, all right, we have a job to do, and basically the job is called synthesis. You see, that's the first task. And synthesizing a circuit means in some way going back from the equation that is expressed as in VHDL, now going back to the circuit. So we will inspect this circuit, and this circuit is going to be called the RTL schematic. RTL is a name that is it stands for a register transfer level, but now at this time this is for you just in a schematic generated by the machine in a way that we do not have to go drawing that kind of picture anymore, because the machine is going to do so for us instead, right? And that is going to be a great advantage. All right, let it be the machine, the device that draw these kind of pictures. So this is what we are going to do. We are going to run the synthesis, and we will keep an eye on the RTL to see more or less if what the machine has understood looks like the original circuit from which we have extracted the equation. Pretty much like Wolfram Alpha, when instead of truth table we do such a thing as logic circuit. What the machine produces, the engine is a circuit, right? So here is the same idea. After synthesizing, you see, you will have a kind of a schema that you can print and comment and keep an eye on it to see if it's looking like this. And well, once you have a circuit in a computer, now the next step, as is the same as when you were using Proteus, you have to simulate. You have to go applying values, D8, D0, D1, ones and zeros, so you can reach the output and you can calculate, by simulation, by simulation again. This time using VHDL techniques for simulation, you will get the truth table in the same way that you did using Proteus, applying ones and zeros, a stimulus to the inputs, so you get the output. And if it's possible, let's consider all the stimulus here, the 16 of them, from 0, 0, 0 down to 1, 1, 1, 1. So this is the next step. Basically, after synthesis, we have to have another project here, which is going to be a simulation project. And to do so, we will keep the VHDL environment all the time. So we're not going to go anywhere else but using VHDL all the time. And to do that simulation, what is required is what is called a VHDL testbench, That is the word, testbench. Which basically, a testbench is nothing but, you see, it is simple to design. A testbench, it's just a closed box, an environment that is completely closed. And inside this box, we are going to place what is going to be called this, the unit and the test, the device or the equipment and the test. The unit and the test is going to be in the center of this test bench. By the way, it's going to have a name, right? Let it be like this, circuit W, because it's like this, you see, circuit W, this is the test bench for, so let it be circuit W underscore TB dot VHD, because this is nothing but another VHDL file. But now you see it is this enclosed fixture, and inside the unit and the test, which is nothing but the circuit W that you know very well, the circuit W, the one that you like to go testing, right? In which way? Well, considering some signals, and the signals are going to be connected to a given process to stimulate the inputs, D1, D0, A and B, and so the simulator will extract the output in time, right? That is the point. The simulator is going to generate the timing diagram. So that is the job for us here, to inspect the timing diagram. You will study that concept for many projects now because it's fundamental. It is the kind of the W and all the inputs, you know, in time. Let's inspect how the output and the inputs are going to be once the time is evolving, right? So that is the point. So to watch this timing diagram, we have here another tool, you see, in the output. So in the output we have to have the, you know, the set of inputs and the output as well. So this is what we are going to do. We are going to apply a stimulus in the inputs, whatever they are, if possible the full truth table, you know, and then in time we will see what happens with the output. So which is going to be the output from this circuit, right? So, and finally from this inspection at the given time, you know, we will extract the final truth table. So this, that now using this explanation, it's quite, you know, new and confusing. It's going to be clearer perhaps when we do that now, you know, step by step using the right tools. By the way, the tools that we can use here are from several vendors. We can use Lattice Semiconductor. Alright, Lattice Semiconductor tools, because they have both complex programmable devices and FPGA, field programmable gate arrays, or Xilinx tools, or, you know, Intel tools. Intel tools like the ones that we are going to use this semester here, which are going to be Quartus Prime. Quartus Prime for the process of managing the project navigator and other features. But apart from the Quartus Prime, we will use the simulator, which is going to be from another company, Mentor Graphics, but is attached to the Intel Quartus Prime. So this is called ModelSim. Alright, you know, another free tool in this case, which is the light edition, but is for this thing of going through the final simulation, you know. And now perhaps the last word here is that for getting this ideal truth table here, that is what we want now, we will simply go through, you know, a simulation, but this simulation is going to be simply functional, right? This means that we are only interested in the ideal truth table, not something real. So, well, that's okay for now, because then when we go advancing here through the several projects, we will develop the gate level simulation, which is the real one, and that is on the circuit that is really downloaded on the target chip. Now, a functional simulation for verifying if the circuit has the truth table that we like to, it's okay. So that is more or less the environment, and then here there are many things to explain, but we are just at the beginning. So now if we accompany this with the presentation screen, you know, going through the process step by step, capturing my computer screen and trying to record that is going to be enough, right? So let's just start. From Digsys web, jump to P1, and in P1, where you have the different analysis methods, down there probably you find something about the method 4, like here, okay, in the lab 2. Okay, because this method is already connected to the next project P2. Okay, now it's here. Well, with the aim of introducing the VHDL to you now, just now, from the very first circuit. In this way, you can keep using it all the time. So here you are, the method 4. And the most important thing here is that just to speed up everything, you already have the circuit W in VHDL. So the only thing for you to do is to copy and the link location, save the link as, you see, you can save the circuit W as a file with the same name, you know, instead of finding something similar and adapting it, this time you already have what you want, which is the source file scikit-w. So you can copy it as it to the right place. So this is going to be the project P1 and a folder that is going to be named the same way, scikit-w. So here is where you are going to copy the scikit. So I did that already, so save it like this, and that's okay, okay? So now that you've got in your folder the scikit-w, you can edit it, okay? Because instead of editing it this way, you see, in black and white as a typical text file, let's view this file as something that is enriched with coloring, because everything is going to represent different information. So if you click the scikit-w, which is already in your folder, you see it now in colored, okay, in colors. For example, color blue for key words, you know, statements and special words in this VHDL language, and then inputs, for example, are the ones which are kept black, and then some information is colored in red, and then you see information which is green is considered to be a comment. All right, so there is always a heading here, a heading pointing to the web when you find this kind of stuff. But the most important thing is that we will edit this kind of files using, you know, the Notepad++, okay, an enriched text editor. This is what we are going to do all the time, because you see, you can identify the language in which the text is edited, you see, and here you see clearly that the machine identifies the VHDL language as one possible language to use. So this is what is happening here. You have the file colored in different sections, right? So the first section, the most important thing here is the entity section, something that you see here very well. So the entity is nothing but what we call the symbol, right? The symbol of the scikit consisting of simply inputs and outputs and the name, right? scikit-w, and some inputs and some outputs. That's the symbol. All right. So this is what you've got here in the entity definition, the name of the scikit, and then the definition of every port or every input and every output. And it's that easy. For example, A, B, those are typical inputs, single wire inputs, so are defined in this way in standard logic type. Standard logic means basically for you that you have zeros and ones here for the A and B. Okay, these wires will carry only zeros and ones. And then, for example, here you have a variation. D, in this example, is considered a standard logic vector, 1 down to 0. This is because the symbol is the symbol 2. You see? The symbol is organized like this. In some way, you see the D is packed in what is called a vector input, and that makes a different definition of this entity in the file. For example, if here, in this case, you have D1, D0, A, and B simply inputs, standard logic, right? In the other symbol, in the symbol 2, the A and B are the same, but the D1 down to 0 has to be represented like this. D is going to be, you see, colon, input, a standard logic, but now a vector, an array, you see? And this vector is of a given size, this time 1 down to 0. So you can use capital letters or small letters, that doesn't matter. VHDL is not sensitive to this. So you see, This is why we will fix the symbol, whatever it is, like this or like that, we will fix the symbol from the very beginning of every project. Because if you have slight modifications in the symbol, you have to do that already when you translate the symbol into the entity in VHDL. You see, one thing is to do that, and another thing, different, absolutely, is to do D1 colon D0. So you see, is another way to do it, but you know, this time you are considering D1 and D0 as individual wires instead of a vector, taking the other symbol, the symbol number 1. And that is important because then the equations differ a little bit. You see, when you are using D as a vector, you have to use the bracket, you know, parentheses with the index of the signal. So D1 may be like this when it is a vector, like in this example, or D1 may be like A or B when they are considered as, you know, individual wires. So that is very important because, you know, we will fix the symbol so that we are not going to have problems in the interpretation in the symbol in VHDL. Okay? So that's it. The entity is inputs and outputs, and then it goes the architecture, and the architecture is, in this case, something as that simple. More or less exactly the same equation that you already had in Wolfram Alpha. So this is an advantage for you. You've been typing equations like this very well in Wolfram Alpha. So now you see the VHDL is practically the same. Okay? So that's the starting point of the development now. We have to do that translation of the equation into this special format and place it into this architecture. Okay, so for now is okay. So now it's time for starting the synthesis tool, you know, the electronic design automation tools that is going to take this source file. So now it's time for switching off this file. Let's close the file, right? Save it, and now you can go to the folder, and here you are the file, right? So very good. So now it's time for you to find, you know, let me find the desktop, show the desktop, and here I've got installed the Quartus Prime. So I double click this device and I've got this window, and this is going to be the development environment. Okay, see the IP catalog, you can get rid of this window. Sometimes you have windows that are not of your interest, but basically the task and the compilation and the project navigator window, that's okay, and the console as well, right down there. So now it's time. So what you see here is an empty project. Very well. So now it's time for starting. You see, file, new project wizard. So this is what we are going to do, a new project. So next, first of all, we have to type here the working directory. And you know very well which one is this directory. L, CSD, P1, scitw, and this is the working directory. All right, select the folder scitw. Now, which is the name of the project? We will do that all the time. The name of the project is going to be the name of the circuit of interest underscore PRJ, right? Like this. And then you have to attach a new information, which is the top entity. And the top entity in this case is simply scitw. So you will do that once and again. Okay, the project location, this is the name that we will attach to every single project. The coder underscore PRJ, keyboard encoder underscore PRJ, so this time is scitw PRJ. And the name of the top entity, which you see very well in the schema, this is the top entity name. So this is the name that you have to pick up here. And do that systematically. Don't try to invent any other thing, but do that all the time. Especially if we have to go correcting your work, It has to be like that, because if we find here different names and different options, that is going to be a complication for everybody. So attached to the rules here in CSD, this is the naming convention, okay? All the time the same way. So you say next, let it be an empty project, and now let's, because the device is pointing to the right place, so let's say add all, and now you see the file name scikit-wbhd, which is the source file that we've been editing, has been identified correctly as type BHD file, and it is right. So this is the one that we have added to the project. It was there in the folder, right? So very good. So now you say next, and here is time for picking up a device. For example, you can pick up the Cyclone 4E or any other, you know, device. For example, the Max 10 FPGA, the same way. And what is this exactly? Well, this is the chip, the square chip that you have in the demonstration board. So you see the same Max 10 has multiple versions, and the one that we have to select, you know, is the one that we have in the lab, and the one that you could use for your step number 6, which is downloading the configuration file to the real board. So where is that you are going to find this name, the exact name that corresponds to the Max 10 that is populating the developing board. So you will find that very well in Digsys web page, all right? And here, for example, electronic devices and companies. In this tab, you have everything. So, for example, you go down to companies, Intel, and here you are, the Max 10. So this is the chip that you are going to use. Control, you can copy this name, right? Here is where you have many information related to chips and technologies and vendors, Xilinx, Intel, Cypress, Lattice. So we will go time to time. We'll go back to these pages and we'll talk about this. So we could have used the Max 2, which is a complex PLD, is not an FPGA, or we could use, for example, this Cyclone 4, the same, right? And we will do that another time. So, for example, this Max 10 is okay. It belongs to the Thoracic DE10 Lite board for training, you know. So very good. Let's go back to the Quartus environment and now paste the name here, and you see from the long list of devices that you had here, now it's a single one. So this is the one that we are going to use, right? 7G. So if you take the 7, you see you have many possibilities. So it's going to be 7, and now the G is an extra letter. That's okay. So this is the chip. This is what we call the target chip. So you say next now, and now this page is also important. You know, this window tells you, for example, for simulation, which is going to be the tool that you are going to use. And the tool has to be all the time, for all the projects, ModelSim Altera. Okay, and the format is not the Verilog VHD, which is equivalent to VHDL, but VHDL, right? So this is something that you have to prepare. The other tools are going to be by default the ones that are here in Quartus Prime, but not this one, okay? The simulation is going to be carried out by means of this tool from Mentor Graphics that is called ModelSim Altera or Intel Edition, right? So you say next, and now practically you have the summary of the project that you are managing now. So you say finish, and the architecture is built. You see, the project navigator is in charge of analyzing the source file and trying to detect what is going on here. For example, the Max 10 has been identified, and then the top entity scikit-w. So now it's time for what? Well, it's time for, you can inspect the file now the same way as before with another set of colors, but you know, it's the same thing. All right. the entity and the architecture. So this is the file that we will transform now into a circuit. We will synthesize a circuit here from this source file. Okay, so this is going to be carried out using this star compilation, right? You click this button and now you see several tasks are going to be performed sequentially until the end. You see the first one is the analysis of the file that you have input as source file. So it takes a while, right? Even a circuit like this, it takes a while, but whatever, in the end you will have, if possible, 0 errors and your design completely finished. All right. So the synthesis project goes advancing. You see you have different sections in this process. Okay. So basically now we have interest in this analysis and this initial synthesis, right? So if we like to see the schema, okay, we can see that this schema appears here as the RTL viewer, right? Netlist is equivalent to schemas and viewers is equivalent to, you know, a window where you see the schema. So you see RTL viewer and technology viewer, those are the ones that we have interest, and in this project especially in the RTL basically only. So let's finish the machine, the final steps of assembler and timing analysis or whatever else is here left. If you have a faster computer, this process goes faster naturally. Okay. So very well, it looks like that in the end I've got 0 errors, and that is the most important thing. 0 errors means that I've got the circuit I want. So now if I like to see it, I can go through this task list of, or instead I can go to tools, and here I can see the netlist, the schema viewers and the RTL viewer, and that's my option here. You see, I've got a window with the schema synthesized. So this is the circuit. If it is not exactly the one that I've got in the whiteboard, it's not that important. In some way or another, the machine has you know, realized a circuit which is pretty much the one that I had typed in as an equation, right? So this is the RTL view. So this is a picture that you can very well copy in the clipboard and saved later for annotating and documenting. All right. So it looks like that we have a circuit. So now if we have a circuit, we have to start a process of simulation of this circuit. Okay. By the way, before going to the simulation section, I have to show you the other circuit that we have here. This is the ideal one, right? You see, the ideal one, as if it had been written in the blackboard. Very well, the ideal circuit. Then there is the other one, which is from tools the same. You see, netlist viewer as is the technology view, right? So you can click the technology view and you have another circuit. Look at this, it's completely different in some way or another, but you see you have buffers, input buffers attached to every input, but in some way you have 4 ports that has been used as inputs and another port which has been used as the output, and you are using a buffer, and then here the logic cell is the device that is used by this max 10 FPGA to solve the logic. So you can click here sometimes and see what is going on, right? So you see the circuit that has been implemented indeed is this one, you know, just another version. Perhaps it's simplified. So indeed, the circuit that has in the end simplified by this long process of synthesis for this target chip is this one. And this one perhaps is different from the initial one that you had on the blackboard, right? So here you are, one circuit, the one which is synthesized for real, and the other circuit which is ideal. You see, look at this. The ideal has to be what you had in mind in your VHDL, right? But the technology view will depend on the devices that the FPGA has internally to generate circuits. Okay, basically lookup tables and RAM memories and the like to implement this logic. We will talk about that in the next projects to come. So, but now, by now is okay. You see, one circuit which is the real one, and the other circuit which is the ideal. That has to be the one. I insist on this, right? The one that you have input as an equation. So very well, this is the end of the synthesis. This is the end of the development section. Here you are a circuit, you've been developing the circuit. So very well, now it's time to go to the simulation process, okay? This is our Quartus environment. And here is where we can inspect the RTL, and now we will continue towards the final simulation process. And if we go back to digsys webpage, we have to see it, right? This is the sequence that, for example, is developed in this lab 2, and this is exactly what we did, you know, generating the circuit W project and inspecting the RTL and the technology view. So very well. Now it's time for simulating in ModelSim Intel edition or something similar from Xilinx or Active HDL that goes with Lattice tools. But this time we will use ModelSim. So this is what we are going to do, a new project in ModelSim. But the very idea here is this one. So, as we have explained before, we have to have a closed entity with no inputs or outputs, but a closed entity that is going to be the test bench fixture. And here in the middle, there is the component and the test. And so our aim now is to apply signals by means of a process and to inspect the waveforms generated by the simulator. And fixing what is going to be a constant, you know, the min pulse constant is going to be referring to the minimum time a signal is stable and when it is applied to the component and the test. So this is the fixture that now we have to have in VHDL. You see, this is the blackboard schema. So now from this schema, we have to switch, or we have to translate this schema to VHDL. And how are we going to do that? Okay, we are going to do that automatically, okay, by means of a test bench generation from the Quartus environment. So you see, you may very well select the chip, and then you can go to processing, and you may say start. And what exactly you like to start now? You like to start down there, which is a test bench template writer. So you click here and the machine starts working, generating for you the skeleton of this fixture for test benching, right? And where is this file located? Well, in the proper folder. If we have done that very well, you see we have a circuit WBHT, T stands for test. So we have the scikit-w VHD in the corresponding folder simulation ModelSim in the project folder. So let's go and do that job of going to simulation ModelSim, and now let's rename this file to be scikit-w tb, okay, and instead of VHD let it be VHD. Let's do that all the time. Change the file extension. So now we have a VHDL file, but with this particularity. Is a test bench for testing the scikit-w, and this is the naming convention that we will use all the time in this digsys platform. Okay, so and now what goes next is to make it easy. Let's copy the file, okay, to the scikit-w folder. So paste the file here alongside with the other one, which is the component and the test. So you see now we will have now a simulation project that will consist of two files, the component and the test, scikit-w, and the test bench itself. Okay, and perhaps now, if you like, it's time for inspecting this skeleton test bench that has generated now Quartus Prime. So you open it, you will see it is a VHDL EDA, okay, and here you are the entity. You see the entity is just a box, no ports, and then the architecture consists of several wires and the component. You see the component and the test scikit-w, and here is the beginning. The beginning is the declaration, the instantiation of the scikit. So let it be like this. Do not modify anything now, and go down to the process init. You see down there you find a process init and a process and the process init and a process always, right? But you see both processes are very empty. There's nothing in it. Here is where you have to place your stimulus for the 4 inputs that you have in your scikit. Okay, so how is going to be done that thing? From scratch? Are we going to start typing in here? No, that's not the point. We have always something similar to copy and adapt. So let's go to the web and find it. If this is the section devoted to the step number 4 on testing, right? Here you have a similar test bench. So you click here, and now even it is in black and white, you see that is a very similar scikit. Okay, so let's start copying the constant min pools that goes, you see, before the begin section of the file. So let's copy this, Ctrl+C, up there into our project. So you see, after the architecture, before the begins, here is where we're going to place the constant. So min pools is going to be, for example, I don't know, which value? Well, you know, we are just translating a schema. Which schema? Well, the one that you probably could have developed in a paper, right? Which paper? Well, here you have a paper now, or in this digsys page, you have a schema here in these some notes. This is the schema, you see. This is what we are trying to do now, placing this process for stimulating the scikit, and this is what is in our mind, you see. We like to very well verify that the scikit is this table, but we have to do that, you know, applying inputs in time. Okay, applying the D10 and applying the A and applying the B, giving them different values. Now, because this is the very beginning, doesn't matter if you apply all the values, just some of them to see that it's going to work. So if you do that, okay, you see that for a while you have the signals stable and constant for a given value. For example, from the starting point of the simulation up to this point, up to here, you have 0, 1, 1, 0. So you are inputting the value 6. Okay, and what is what you are expecting? Well, the calculator, you know, the simulator has to generate a 1 for the W signal. And then what? A 1, because you know it's not in this list of max terms, but is a min term. The 6 is a min term. So this is what you are expecting. The same for the next vector. And the next vector you see appears when the D 1 down to 0 changes from 0, 1 to 1, 1. And it lasts until the A changes as well, from 1 down to 0. So you see, for this time, for this specific time, you are applying to the circuit 1, 1, 1, 0, 1, 1, 1, 0, and for this value you are expecting another one, and so on and so forth when you go and change the values of the inputs. And sometimes, for example, it happens that you are applying 0, 0, 1 and 1, and this is the combination 3, and you know that for this combination 3, because it's a max term, you have to have a 0. So you know what is going to be the output of the circuit, and that is good. You are preparing this in paper, right? If not the final solution, because this is what the machine is going to give you. But you see, as here, you know even the final solution, because you know it from other methods. So that's all right to have it all clear, if possible, in your paper. Because now, if you have this in paper, it's only about translating this diagram, this timing diagram. Let's translate it into VHDL. And you see, the translation consists of applying different values to the inputs in time and keep them for a while. You see, how long do you have to keep the signals? Well, you see, for example, this is a minimum time, or that one here, this time is even smaller, that one, just a little bit smaller, right? So this is what may be for you the min pool. So you can assign these min pools a constant, for example 20.2 microseconds, because other times can be derived from this constant. For example, this long time here at the beginning may be very well, for example, roughly 5.5 times the constant min pools. Okay, so you can refer here all the times in which you are applying vectors. All this instance of time can be referred to the min pool, and it's going to be that way all the time. So now perhaps it's a little bit confusing, but when you see this in VHDL now, and from now on, you will see that this is not difficult. So first of all, let's annotate these min pools, 20.2 microseconds, okay, in the file. So this is what we are going to do. The constant is going to be 20.2 microseconds. So this means that we will run the simulation for how long the simulation is going to run. Well, for example, if this is 20.2 microseconds, you need at least 16 times each time, or a lot more if you have values that are lasting more than min pool. So, well, why not 1,000 times this? 1,000 times 20 microseconds is okay. So you can very well say that you will run that for 20 milliseconds, or 20, if this is 20 microseconds, 1,000 times, very well 20 milliseconds, that's okay. So this is the final running time of the simulation. Okay, so this is for the constant. And now let's go down and pay attention to the digsys schema that belongs to this example. You see the VHDL test bench example template, which happens to be of the similar circuit W. Let's see if it's the same or not. You see here the declaration of the device. Well, it's the same because the D has the same vector logic. So very well, it's the same circuit. So this means that you very well can copy it as it is. So let's copy it, right? Let's copy this process. So let's go from stimulus process and let's copy the vectors to the end of the process. Control C. And now let's go back to our circuit, delete the always, delete the process in it, and now in this white space, can Control V, what you've been seeing as an example in the web. So what is exactly what you've been copying here, you see? So let's inspect it a little bit to understand more or less if it's sounding to you or not. So you have a process now, okay? The process begins like this, just waiting for a while. Okay, you see, you are waiting for 1.5 times mean pulse, which is about 60. You know, this is 70 microseconds or something. That's all right. It means nothing, just a starting. Then what you do is to start the stimulus activity. For example, here you are fixing an input vector. D1 is 0, D0 is 0. A is assigned value 1 and B as 0. So what are you inputting here is the number 2. So the number 2, you know, it has to be 0 because you know that from the other methods, 1, 2, or 3, because it's the same circuit. And then what you do is to wait for a while. If you like to do exactly as you have here in the whiteboard, okay, if this is what you've got in your whiteboard, you can apply 0, 1, 1, 0. Okay, you see that? You can very well translate exactly or approximately what you have in paper. You are starting the simulation at this axis, time equals 0, and now you are applying for 5.5 times mean pulse the vector 0, 1, 1, 0. So this is what you are going to do here. You see, 0, 1, 1, 0 for 5.5 times. That's one way to do it. Then you are changing values. Here you see it is applied the vector 0, 0, 0 for 3.1 times mean pulse. But if you go back to your whiteboard, you see that now you are applying for or less, 1.2 times mean pulse, 1, 1, 1, 0. So very well, you are applying 1, 1, 1, 0. You see, this is what you are applying. Here it is very important as well to annotate comments. Explain what you are doing here, you see. So I'm applying the vector 1, 1, 1, 0, and I know that it has to be 1. Like this one has to be 1. Okay, I know that. Then you can go the same way with the next, you see, and you're applying this 1.1 times, and then you can go to the next, which is this time, you see, 1, 1, 0, 0 for about 2.2 times mean pulse. That's okay. So now 1, 1, 0, 0, 1, 1, 0, 0, it has to be 1 again, and you apply that, for example, for 2.1 times. And then the next is that one which is exactly mean pulse, 1, 1, 0, 1. This is what you are doing now, 1, 1, 0, 1. So 1, 1, 0, 1 is number 13, is another one, and you apply these for 1.0 mean pulses. And then you continue. This time you are applying 0, 0, 0, 1 for example, 2.3 times mean pulse or something like that. It was 0, 0, 0, 1, 0, 0, 0, 1, okay, 0, 0, 0, 1, and this is for 1.1 or 2. Doesn't matter very much, so it is again a 1. So now the first time is going to be a 0. Now you are here, right? And here you are inputting 0, 0, 1, 1 for a period of time, approximately 2 min pulses. So you will do that now very well. It's going to be 0, 0, 1, 1, and so this is the vector 0, 0, 1, 1, the combination 0, 0, 1, 1, and this has to be finally a 0. And if you like, you can input the last one, which is again a 1, and this is 0, 0, 0, 1 again. Okay, there is not a problem repeating the vector. You are simply saying here, trying several vectors. Doesn't matter if you apply the same vector again later in time. So 0, 0, 0, 1 is what you do. So you did that before, so you can copy it, Control C down here, right? This way. And so on and so forth. So normally when this is going to work, after that you see that this is working, is your time to arrange the vectors that you are inputting here in a way that you are covering all the 16 combinations. But let's do that later. Now it's okay with these simple inputs. It's okay to check if everything is going to be all right. So you see the job of generating the test bench. So let's repeat, okay? Let's save that, save, and look at this. What we've been doing here is simply inventing this schematic that belongs to a test bench, and we are translating to VHDL the activity that we had organized in paper. And don't worry very much, because we are going to do that all the time. That's the method that we have chosen to invent our circuits all the time. So you see, it is very practical, because indeed you are talking about the text file, while indeed it is a graphical thing that you have in your mind and in your paper. So it is going to be very convenient, the VHDL idea all the time, to make modifications and variations and invent different circuits from similar ones, just like this, modifying a text file, but not because it's software or anything like that, but because it's in a schema, you know, a schema or a timing diagram that has been converted into a process. So that's the way we will do that once and again and forever. All right, so look at this. Now we have the source file, which is the test bench, as well as the W, which is the component and the test. So if we have both, now it's time for going back to the desktop and running. If it's here, I don't see it now, but you can run the ModelSim, okay, FPGA Starter Edition, Intel FPGA Starter Edition. This is the one that we are going to use as an EDA tool for VHDL simulation. So let's click it, okay, and let's start again a new process from scratch, but this time for simulating. So ModelSim has this layout, okay. So very good. So now another way to go to this point, okay, file, I have to switch off something that was here before. So close all the projects. So this is the empty window for this ModelSim environment. In some way you have here the console, the transcript console, and here you are the libraries, and that's empty. So let's start, okay, let's start. Another way to reach this software is, I guess, from Quartus Prime, right? From Quartus Prime you have tools, right? So you see, before we have, previously to this, we have run the tool that was the netlist viewer. Remember that? So now, if you like, you can run the simulation tool from here if it's organized correctly, it is configured. So if you click the RTL simulation, you will reach a similar window, right? So the simulator opens that way. So probably now I will have two of them. And this is the right one. You see Intel FPGA Starter Edition. The other one was from the Quartus 2 instead of Quartus Prime. So let me switch it off. It is this one. Well, let's switch them both because now I'm not sure which one is the right one. So only one is okay. One single edition is okay. You do not need too much of them. So clean the screen is possible. Yeah, so let's start again now that we see that is working fine. You see, we have Quartus, and do it like that because it's better. Run the simulation tool, the RTL simulation. That is going to be easy if properly configured, right? You only have to give here in the name of the software that you are launching from the desktop. So here you are, right? Very well. So let's start. File, new, right? New project. Again, it's a new project for simulation. So the project name, right? Which is, well, let's find the location if you like first. The location is the one that you know. It's scikit-w again. So this is the location, scikit-w. Okay. That's the location, scikit-w. Then the project name now, it's a simulation project. So it's going to be scikit-w underscore functional sim all the time. You know, every time that you go simulating a functional simulation is going to be like that. The name of the entity and the test underscore functional sim. And then the default library where the device is going to be placed is the same, work functional. Okay, that's the name of the library. So we will do that all the time. So don't worry very much. You say okay. And now it's very similar to the other one. So add an existing file like before. We have the chance to have both. Okay, so we are not going to improvise here anything, but the files already exist in the right folder. So you add existing files because we did that with the Notepad++. So let's browse, and here you are. Because the machine is pinpointing to the right folder, you only have to select both files now. You see the testbench and the W together. Open them and say click OK and close. You have both files here, you see. So now it's time for, because you see the question mark, the status of these two files are yet unknown for the machine. So now it's time for you to click this tab, compile all. So if everything was solved fine, you click compile all, and you have to have, instead of question marks, the machine has to do the job and identify them correctly. So now you have green ticks, you see. So this means that the files are with no syntactical errors or anything like that. They are right. So when you've got the two files right, that means that you have already the testbench completely organized. So it's time for, let's go back to the web, because this is what you've got now. Let me explain it to you. This is what you've got, right? This is a schema with the two circuits, the testbench, which is a circuit itself as well, and the component and the test. You've got that now, so now it's time to click run the simulation, because these values are going to be applied to the circuit. So let's do it, right? And you are going to run the simulator here, simulate start simulation. That's the way. And what exactly you will simulate? Well, you see the work functional. But what exactly about the work functional devices? The scikit-w, or instead the scikit-w testbench? This one, right? This is the one that you have to simulate, right? That's the one which includes the process of stimulus signals. So this is the one that you have to click. You say OK, and now the machine starts doing what? Well, if everything goes right, you have to have a new window where you can place the logic diagram, right? Not the logic diagram, but the timing diagram. So everything went fine. Everything looks fine. You see, nothing is red, so this means that everything has been fine. So now is your turn. You have to add, you know, or you can select everything here, okay? And you, with a right click, okay, look at this, with a right click on the circuit, you see, the circuit contains it all. You see an entity, the entity is the circuit and the test. So this is the top, you see. So you select the top with a right click and you say add to wave all the items in region. That's the fast way to do it. So you do that thing of add to wave all the items in region, doing that selection of the top entity with a right click. So you click this and the machine has to make it possible for you to see a graphic window, which is the wave window, right? So very well. So this is the wave window. So now it's time for you to run what you know that you know how long you have to run the simulation. You see, the simulation has started, but has not gone from time 0 yet, has not advanced, not even a picosecond. This is what you are going to do now. You see, you have to go to the console and you have to simply say run. For example, what you know was 20 milliseconds, 1000 times the minimum pulse, something like this, or 2 milliseconds. That's going to be okay, the same. You do that, and now the machine do the job of generating signals. You see here you have the signals, and if you like you can separate them, because if you like you can include here, you can add a divider or something like this, output for example. Let me say that thing. So the output is W, and you see now the D is the third signal, and this is not the way you have organized it. So the D has to go to the beginning. So now you have, you see, D1, D0, A and B. The signals ordered in your way and the output. And what is what you see here? Well, nothing at all in principle. What you see is the last simulation time. So what you have to do now is to select this graph and click zoom full, right? If you click zoom full, now you see you have a long period of time. You have run that too much time, but that's not a problem. You see, you can move now the cursor to the very beginning and zoom with the cursor and the control. So you can control, and with a roller and your mouse, you can do this job of observing very well what's happening. You see, this is the output, right? And those are the inputs. So very well. You see, let's check something. For example, now at this time, with the cursor at this position, you are inputting exactly 0101. No, 0110. You see the number 6. This is exactly what you have decided to do in the test bench. And the output is right, is 1. You can advance now to the next vector, which was this here, you see. And now you are applying 1, perhaps it's better like this, 1110, the combination number 14. And this combination is generating a 1, which is right. And then another combination, 1100, the 12, is generating a 1. And then again this 1. 1101, which is the 13th, is generating a 1. And the next one, 0001, combination is generating a 1. But look at this. 0011, which is a 3. The third combination is generating a 0, which is exactly what you've been expecting here. So you see the machine has ratified, has generated, a waveform diagram, a timing diagram, in which you can represent all the 16 combinations, and this is the tactical thing here. You can go from the first combination and advancing until the last combination. In this way you can go in a sheet of paper annotating the truth table as you did in Proteus. It's exactly the same thing, but now you see perfectly organized in VHDL using professional tools, industry standard tools. Okay, so what goes next here from this kind of diagram, apart from capturing it, you can capture the diagram and you can take a picture and make annotations the same way that you had here in this example picture in P, the picture number 4. In P1 was about something like this. You see, now you can recognize what we've been doing here. The inputs, the outputs, and the cursors in time advancing and showing you different possibilities of the inputs, and so generating, even with a different color, the signal of interest, which this is the output. So you can go and generate the truth table in this specific case, because it's an analysis, right? So because it's an analysis, apart from this picture, you need to do that kind of diagram in a paper. You have to have this D0, D1, D0, A and B, and W and what. For example, the first combination was 1, 0, 1, 1, 0, a 6, and you get a 1. What was next? This one, 1, 1, 1, 0, right? 1, 1, 1, 0, and was 1. And then 1, 1, 0, 1, 1, 0, 0, and was again another 1, and so on. You have to go like this until you get, for example, this combination, which is 0, 0, 1, 1, and this gave you a 0, and so on, right? So the truth table, this is what you want from this analysis exercise using this kind of tools, right? Naturally, perhaps, well, I cannot explain you all what is here in a state, we will develop that in many more recordings, and especially in class sessions and lab sessions. But now that your test bench, look at this, is not complete. You see, the test bench is not covering all the situations possible, only 6 or 7 of them. So now, naturally, you like to stop the simulation. Okay, you may even you may like to stop the simulation and start again with a new set of vectors. And you can do that very well here, I guess. Okay, you have the test bench here. So now you can edit this file because it's the same, it's colored. So you can add a new vector, Control C, Control V, or in some way you can edit these. Well, perhaps looking at the project, sorry. So let me see if I'm all right now. If I can click here and I can edit this file, adding another vector or organizing them correctly. So this is going to be the first one. Okay. And I can copy that again. And I can change that from to be 1. So if I like, I can do that now, because now the machine is working. So now is the right time for finishing the problem of getting all the sequence of the 16 combinations to the end. So you have now a new file. You save it, right? You save the file. And once the file has been saved, probably you have to simulate, but stop, end the simulation or restart. I don't remember now. You better end, if you like to be sure, but you can reorder this from here, relaunch and restart. So you can end the simulation. You see, the machine has identified that the file is different. Okay, so you can recompile that. And now that the file is okay, you can simulate again. Okay, start the simulation or restart. Okay, doing that from scratch as before, or basically you can do that again with a restart. Okay, so this is your diagram. Okay, your diagram is here, so you can do the same thing of adding all items in region to the wave. So this is what you've got. And finally, you can, well, if you are getting tired of doing this arrangement of waveforms and introducing the dividers and the like, you can save the template of this waveform as well, right? You can do that, save the format. You can save the format, okay, as a do file. And then instead of opening from scratch, you know, the wave diagram, you can open this file and the waveforms will be in the order that you like best. Okay, so now it's time for you to run again. You see 2 milliseconds is too much. If you do that, 200 microseconds is okay. So now you can go back to the circuit and you can zoom it all. You see, but it's not that, it wasn't that much. So you can run 2000 microseconds. Now it's going to be right. So you see, zoom all, and here it is where you are, the activity of the signal. So you can change the properties, the format, or the radix and the color. You can change the properties of the signal, for example, the wave color, okay, can be red if you like. So that's a kind of a circuit that you may like to print using your snipping tool, okay, and this is what you like to place in your report file, right? And here you are going to annotate using a paper and a pen. Here is where you are going to do that thing of annotating. All right, for example, here I'm inputting 0, 1, 1, 0. So this is the 6, and the signal output, you know, is a 1. So this is the kind of annotations that you can just, in this way you are customizing your results and in telling us something very important. You see that you are doing it. So you are in some way learning by doing the job. Okay, so that's the recording.